So we're done with two topics in the beam chapter. The first topic we talked about before the exam one was beam interpolation. Basically, we assume that if we know the nodal degree freedom, let's say for one element, V1 theta 1, V2 theta 2, we know how to do the interpolation to find the V and theta at any point in between. The second topic we talked about in the last class was, let's say, back to KQ equal to F. So if we know the your structure material, basically is the Young's modulus. If you know the length of the beam, if you know the cross-section dimension, which can give you the moment inertia, so EIL, if you know the K, Stiffness matrix. And if you know the force applied on the beam or a couple applied on the beam. So in the F vector for one beam element, you know the F1, C1, F2, C2, right? So basically now if we combine these two into one topic, basically it means that if I give you the structure, if I give you the force applied, you should be able to calculate the deflection and the rotation at any point within the beam. Makes sense or not? It's basically first step, calculate nodal degree freedom. Second step, interpolation. So, and of course, in the last class, what I did was like very simple example. Basically, we have force, concentrated force applied here. I don't like this color. But we know that for beam problem, it's very common to see that the force is distributed force. Let's say if somehow you have distributed force like this. Let's say if there's a supporting beam of our class, and it carries the weight from the above. And for this beam problem, you can consider it's a simply support beam. It's boundary condition on this side and boundary condition on that side. And in between, it should be approximately uniform distributed force on the beam. Makes sense or not? Since many of you from the aerospace program, so another situation is that, let's say you have the wing. And for one side of the wing, you can consider is a kind of beam. Basically, the connecting point of the wing to the fuselage is more like a clamp situation. It fixes the deflection, it fixes the rotation at the root of the beam, of the wing. And for the rest part, it's free to it's free. The other side is free end. And if the wing is designed well, you should expect that there's a elliptical distribution of lift. Again, it's not like concentrated force applied at wingtip, but it's a elliptical distribution of lift on the wing. And then you need to calculate, okay, what's maximum stress, what's maximum deflection at wingtip, and is your wind box or wind spar structure can survive from this lift, or if the deflection at wingtip is exceeding your constraint or expectation, you need to do all the calculations. So my question is that there are like uniform distributed force, or elliptical distributed force. How to put those force into KQ equal to F? It's not at node anymore. And you cannot put the node everywhere, like continuous every point, right? So because computationally, it takes a lot of time to do the calculation. So how should we do the KQ to F if there's a distributed force? Equivalent force at center.
Like in that, where you do the equivalent force with distributed load.
Okay, so let's do the simple situation. Let's assume that we have a let's do it this way. One beam element. Let's use simply support. And similar situation, I use uniform distributed force. What is the equivalent force? It's not accurate. Yeah, so we should have a better way. So basically what you're doing here is that now you separate to two elements. And now the equivalent nodal force becomes F, which is equivalent to this distributive force, and half of F here, half of F here. This is one type of converting it to equivalent nodal force. So basically you have half F here upward, one F here, half of it here upward, right? You can do the calculation of the class. So to check if it's equivalent, we need to say equivalent of what? One thing we can consider is equivalent work done by the force. So what you can calculate is, let's say for this situation, the similar situation, similar support beam with uniform distributive force, you can calculate for this uniform distribution situation, what is work done by this force. So basically it's integrating from 0 to 1 ds, and this, let's say P, S, and V as V, the deflection caused by this force, right? So this is the work done by distributive force. And the other one is, now for this situation, you have this force and reaction force, and you calculate what the work done by this force and make it to check if it's equivalent, if the work done by the force is equivalent or not. So this is something you can do after class to check. I can give you a conclusion. It's one way, but it's not accurate. So any other idea? So in a general situation, we don't know what is equivalent force. So we just put into equation and calculate what is equivalent force, right? So this is in the chapter 3, section 3.2, work equivalent nodal force for distributive force. For distributive force. So let's start from let's do it better. Let's put as one bin element. And let's assume that it has distributive force Px. Let's put upwards so everything is positive. So let's assume that it has Px. And we have the equivalent nodal force. Since we have two nodes, let's say this is node 1, node 2. And we consider we have the equivalent nodal force F1, C1, and F2, C2. So in a general situation, we just put everything into equation. So basically, we need to find a expression of what is the work done by this one. And we find another expression of what is work done by these two equivalent nodal force. Actually, if you say F and C are two force, then it's 4, right? And then we set these two equal, and we can find what is the equivalent F1, C1, F2, C2 generated by this one. And then we can put in the equation K, Q equal to F. And you just put the equivalent F1, C1, F2, C2 in the F vector. And we're done. And of course, we can go back to what we learned in the previous two sections. Use calculator to solve the nodal equivalent and use interpolation to solve V and theta at any point. So again, so first, let's say for the concentrated force, let's use different color here. force and couple. The work done by this four, we can write as, this is W as work done by this equivalent of force or concentrated force. Of course, you learn from previous class that if I have a point in a structure and I apply force and move upward V, you know that the work done by this force equal to F times the deflection displacement, right? And if I have a structure that I apply couple, let's say it's in this way, and a couple it rotate this much, of course, your structure will not rotate this much, but exaggerate deformation. Then the work done by this moment or this couple should be the C times theta. Make sense or not? So now, since we have F1C1, F2C2, so the work done by these four should be F1 times V1, C1 plus C1 times theta 1 plus F2 times V2 and C2 times theta 2. Right. So this is the work done by this equivalent nodal force. I use different color because we need to figure out this part later. Let's first write V1, theta 1, V2, theta 2, and C1. Don't have color. F2. C2. Yes, thank you. Thank you. Now we need to find expression of the work done by distributed force, and then we have set these two equal. The second equation is for distributed force. W should be equal to, let's say for the field coordinate, in X coordinate, we can write this integration as x1 to x2 for this element. The first node is the coordinate is x1, the second node is x2. So it's integration of this single beam, and we have the P as function of x, and we have the deflection as function of x, dx. So this becomes work done by distributed force in the X coordinate, but we talked about it last class. We derive shape function and everything based on the reference coordinate. So our derivation can apply to any beam with any length L. So let's write this one as integration from 0 to 1 in the reference coordinate. And now your Px, you can write that P as function of S and the V deflection as function of S ds. And we also talked about in the last class the Jacobian between this mapping. Dx should be equal to L ds. So there's an L coefficient out of integral since it's constant. We can put out of integral. And we also, well, this should be the given information. This is distributed force. Let's say it can be a simple situation, can be uniform distributed force. So we can set Px equal to P. So it's uniform distributed. In a more complicated situation, let's say if you want to do a stress analysis of the wing. So you should have the function of P of S, P as function of S, a level distribution. And then you put it into this integration and calculate what is equivalent of force. So PS can be anything. Now, for the VS, actually we had the equation derived in the previous class. So here is VS equal to N1, V1, N2, theta 1, N3, V2, N4, theta 2. So now you can see some trend since we have the V1, theta 1, V2, theta 2 here. And in this equivalent work done by equivalent nodal force, we have the V1, theta 1, V2, theta 2. And in the end, if we set these two equations equal, we can have some coefficient in front of one, coefficient here, coefficient here, coefficient here, and it automatically becomes equivalent nodal force. Makes sense or not? So this is the general idea. For the detailed calculation, I can plug in the V as function of S into this integration. So L 0 to 1 PS. And for the V as function of S, we can write as N1 V1. Of course, the original equation I write as N1S V1, N2S theta 1. But just to save some time, I ignore the S part in the shape function. We know the shape function should be a function of S. N2 theta 1, N3 V2, N4 theta 2 ds. And now we can see that our goal is to put it in the form that rearrange in a way that something, a coefficient times the V1, coefficient times theta 1, coefficient times the V2, coefficient times theta 2. So what we can do is that we have 4 components. So it becomes, let's use the same color, L, P, S, N1, ds times V1. Now this becomes the first component. Second component, use blue color, L, P, S, N2, ds, and theta 1. Theta 1. The third component, V1 theta 1, V2 theta 2, they are nodal degree freedom, so they are constant term. You can take those any constant term out of the integral. I use this color, so it becomes L integration 0 to 1 P S N3 ds V2. The last component, I use this color, L 0 to 1 P S N4 ds theta 2. Are we done? Now you can compare these two. Work equivalent nodal force means the work done by our originally distributed force should be equal to the work done by our equivalent nodal force. So this one and this one should be the same. And I intentionally use different color. And now you can see that F1 V1, a coefficient times V1. C1 theta 1, a coefficient times theta 1. And F2 V2, C2 theta 2. So we have the expression of F1 C1, F2 C2. Our job is done. Right. So if you check the homework, there's a homework problem 3. It asks you to find the equivalent nodal force. I think it's this one, right? If you have a linear distributed force, you need to find the equivalent nodal force. So basically what you need to do is that for that linear distributed force, you need to write the expression P as function S for that one. And then this shape function N1, N2, N3, N4 is given in the previous class. So basically what you need to do is that you need to calculate this component, 4 components. And you are done. Make sense or not? Of course, in the class, I can do a simpler example to show you guys how to do this calculation. The simplest example I can consider is what if it's uniform distributed force? So let's assume if it's uniform distributed force, of course, PS equal to a constant. Let's set as equal to P. Doesn't matter. You can use it later. So a special situation or the similarity situation, if Px or PS, doesn't matter, equal to P. And of course, you can write a PS equal to P. So it basically represents a uniform distributed force. And let's try to find the equivalent nodal force. So F1 should be equal to, now this PS equal to P is a constant term. We can always remove any constant term out of the integral, right? So now it becomes PL integration shape function N1, integrate from 0 to 1 ds. Check connection notes of what is the shape function at node 1. So PL 0 to 1, 1 minus 3 s squared 2 s cubed ds. So basically what you need to do is that calculate integration of this one and integrate from 0 to 1. I will skip the integrate this one and have the expression and then calculate from, you plug s equal to 1, you get the answer. I will give you the final answer directly here. So it should be equal to half of PL. Should not be surprised, right? You have total PL is split half to one node. But of course, since you have the rotation, you have an equivalent couple plot. Otherwise, there's no rotation generated. So the second component becomes C1. Similarly, P constant term take out of integral. And the second term becomes integration 0 to 1 N2 ds. For the shape function of the N2, it's already have L in that shape function, so it becomes PL squared. Integration from 0 to 1. S L 12. The third component, similarly, F2, PL 0 to 1, shape function, ds. So PL 0 to 1. 3s squared minus 2s cubed ds. Half PL, symmetric. So half PL to node 1, half PL to node 2. C2, different color. PL integration N4 ds. And again, the shape function itself has L. So now it becomes PL squared. Integration 0 to 1. ds half P squared. So one is positive, one is negative, basically mean that the force, let's say if force is upward, if force is applied upward, then it basically means that to generate same rotation, one is in this one, one in this way, right? So positive means in the counterclockwise direction, negative means in the clockwise direction to generate same deformation or same theta. So this is similar situation. Of course, we plug in Px equal to P. or PS equal to P. In your homework, you need to figure out what is a PS expression for that linear distributed force. And then you plug in, and of course, when you PS at the function of S, you cannot just simply take it out of integral. You need to put it back here and do the integration for each component, and then calculate equivalent of the force. Any question? So for everything we derived here in this class, in your homework, in your exam, you can use our derived equation directly. You don't need to derive by yourself in your homework, in your exam, including this one. This conclusion, you can also use directly. So let's say if you see distributed force and the distributed force equal to P, you can use this one directly. You do not need to write this part, like derive this whole thing by yourself. So these are the equations you can use directly. Yes, thank you. Thank you. It's, yeah. So basically mean that the equivalent nodal force is, for this situation, the px is upward, it becomes half of PL here, half of PL here. And then we have, sorry, this one is equal to PL squared over 12 in the counterclockwise direction, and on this side, right? And that one is, since it's clockwise, it is negative. And in terms of magnitude, these two should be same. Magnitude. Any question? If no question, let's do an example problem. We assume that we have a beam system. Is clamped on both ends. And we have a uniform distributed force on the left side into the middle point. That is the middle point. And on the right half, we have also uniform distributed force, but it's applied downward. Also, there's a concentrated force applied at middle point. Let's say the concentrated force is F, and we have a couple applied at middle point. I put it as C. For the uniform distributed force and magnitude, both of them, I use P naught. The only difference is one is upward, one is downward. Boundary condition, loading condition, material property. So Young's modulus times the moment inertia, EI, is given here directly, Newton meter square. The length of each beam. Of course, since there's a concentrated force applied here and a couple applied here, you definitely set this one as a node. And then for this uniform distributed force, you find an equivalent node force, right? So definitely we need to put this one as a node. And now we have two elements. So this is node 2, node 1, node 3. And now this becomes element 1 and element 2. And for the L of each element equal to 1 meter. And for the uniform distributed force, equal to 60 Newton per meter. For the concentrated force applied at middle point, equal to 100 Newton. for the couple applied at midpoint is equal to 50 Newton times meter. Couple equal to force times moment. So Newton times meter. Be clear about the unit here. Distributed force times the length of the equal to force. So yeah. So, and of course, the question is find the deflection and the rotation at node 2. And of course, if you combine with previous lecture, I can also ask you find the deflection and the rotation of the entire beam, right? Combine with, but let's say only focus on topic today. Find nodal degree freedom, and the only nodal degree freedom you need to calculate for this one is only the deflection rotation node 2. For here, you know it's 0, 0. Here, 0, 0. So this is the very straightforward calculation. Where should we start? Where should we start? How to find this nodal nodal degree freedom, which is V and theta at node 2. Where to start? Of course, since Young's modulus, moment inertia, L, they are given, so we know the K. External applied force given, we know the F. K Q to F. You find V2 theta 2. Make sense or not? Now for K part, there's no tricky. EIL given, you have the original 4x4 for element 1, 4x4 for element 2. Assembly you should have 6x6. Applied boundary condition you have 2x2. So that one is exactly the same as what we learned in previous chapter, in previous section. The thing that directly connected with our content today is that for this one, and this one, and this one, how to write the force vector, right? How should we write the force vector in the K cubed F matrix equation? We need to find equivalent of the force first. So let's do the one by one. For element 1, well, for the F and the C applied to node 2, in the end, we can just add that term into the corresponding F2 and C2. But for this uniform distributed force applied on element 1 upward, P naught, we need to find equivalent nodal force first. So what is the equivalent nodal force? Anyone? What is the equivalent nodal force? Either the question is too simple, you guys just don't want to answer, or it's make you get confused. Sorry? You need to calculate nodal deflection and the nodal rotation. Right now, we're trying to find the equivalent nodal force. So you can put the force term into the K to F. So what is the equivalent nodal force for? Yes. So let's do it one by one. Let's talk about cancel out later because there's some tricky part. So let's say for element 1, we just plug in this P naught, right? For element 2, since it's downward, there's a direction in it. So negative P naught, negative P naught, negative P naught, negative P naught, and negative net positive. Make sense or not? So as I said, everything we derive in the class, you can use in your calculation directly. You do not need to go through the whole calculation again. So since we can use this directly, let's say for this example problem, what we can do is that I put let's say we have the equivalent nodal force Fi and Ci at each node. So for node 1 caused by this red distributed force, I can put as half P naught and half of P naught here. And for the couple, L equal to 1, so it's 12, negative 12, right? For the element 2, the distributed force, this downward, you just plug in P equal to negative P naught. So what you can write here is that at node 2, we have this is equivalent to F2 and F3. And for the couple, we have over 12 and negative, negative, positive. So I write positive here. Any question for this part? Any question here? Okay, now since you guys are fine with this part, then we can continue our KQTF calculation. And of course, as he just said, there's something cancels out, and you can see that here, positive, negative, so 0. But of course, you need to add this extra term, concentrated force applied here. For the couple, both negative, so there's nothing really cancel out. Let's write the K for element 1. Again, check your action note for the 4x4 matrix. I'll write here directly. We only need 4 components: V1, theta 1, V2, theta 2. V1, theta 1, they're boundary condition, they're constraint. So all the components related to V1, theta 1 doesn't matter. We only need the 4 components: 12, -6, -6, 4. And of course, in your exam 1, I definitely saw a lot of students write complete matrix for each element after assembly, and then apply boundary condition, complete matrix 4x4, 4x4, 6x6. Again, I'm not saying it's wrong, but it's really not necessary to waste your life on those kind of things. For element 2, again, we have 4x4, but we only need 4 components. I wrote a row index here. It should be V2, theta 2, V3, theta 3. And anything related to V3, theta 3, since it's clamped, both of them are 0. So we only need the 4 components here. The rest part really doesn't matter. Assembly. Add the corresponding components. Now this one becomes 24, 6, -6, this is 0, 0, 8. Actually, since there are 2 off-diagonal 0 term, it makes our calculation super easy, right? V2, theta 2. What are the 2 components here and here? What 2 components should I write here? let me see. Negative. Yeah, that should be negative here. Yes. Yes. So basically, for the equivalent force, transverse force, we have this one plus this one plus this one. So it should be equal to F. For the equivalent couple applied at node 2, it should be this one plus this one plus this one. Right. So let's write here clearly. So for F2, it should be plus F, and F is given as 100 Newton. C2 should be equal to negative P0 over 12, P0 over 12 plus C. So negative 6 plus C equal to negative 10 plus 40. This is clear? These should be the two numbers I need to put in the force vector. Any question? Any question? If there's any question, just ask me directly.
For F2, right here, it's P0 over 2 minus P0 over 2. Is that correct? Or it looks like it's
Yes. 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 Another question? Any other mistakes? They are from here and here. Yeah. So basically, this is from, this is equivalent node force come from this part. This is, sorry, couple, force at general term. Equivalent node couple from this part. This green part is the equivalent node couple from this one. And then in addition, we have a external applied couple at node 2. So 3 components. Any other question? Okay. Can give you a final answer. I have a additional question. Let's say if I want to ask you calculate reaction force at 1 and 3, how should we do? And of course, for beam problem, and if it's clamped, we know that reaction force at general term should include a reaction transverse force and a reaction couple applied, right? So basically, again, the standard procedure. Be patient. We still have 6 minutes here. Oh, sorry. This is actually, I don't know, I keep making mistakes. Here. I'm writing this big matrix here. Doesn't mean that you need to have the 6 by 6 components to calculate the F1 and C1, F3, C3. Because if you are very familiar with matrix vector multiplication, you know that these are 0. So basically, whatever in the first and the second column and the 5th and the 6th column doesn't matter. We only need the 2 column, basically 12 components for calculating everything. Make sense or not? So my question is, when you put everything back, well, since we solve for V2 theta 2, you put everything back into this structure matrix equation. Does it mean that this is a reaction force applied by the wall? Reaction force applied by the wall on the right, left and right side. Is this correct or not? Yes, yes. Thank you. Thank you. That's a key thing, because previously a lot of students, they are like confused about what is F1C1, F3C3 actually means. And that somehow they forgot that actually the F1C1, F2, F3C3 should means all the combined externally applied force at node 1 and node 3. And in this situation, the combined external applied force applied at node 1 should be equal to reaction force applied by the wall and equivalent nodal force include couple, from distributive force. And that the sum of these two equal to F1 C1. So that don't get confused like, okay, whatever you get F1 C1, there should be reaction force. No, part of them is from here. So if I write in the equation form, actually I should write this one as R1 plus half of P naught and C1 well, you know, it's a reaction couple. I should use a right. Reaction transverse force applied to the one, reaction couple applied to the one. This is a better notation. Yeah, and similar at node 3. So I just want to make sure you guys understand that F1C1, F3C3, they're not the reaction force. They are the externally applied force applied at node 1, node 3, and they should come from two parts. One is the force applied by the wall, one is from the equivalent nodal force from these three forces. Any question? If no question, we're done for the class. Thank you for coming and have a great day.